Now we will generalize this to arbitrary finite sigma algebra. We'll write this as proposition number 3. Again, let omega script A, P be a probability space. Now assume F1 through Fn are in script A, and omega is the discrete union of those variable subsets. Let script F be the sigma algebra generated by those n sets. The members in script F will be the discrete union of some members here. Then for any real random variable x, this is from omega to r, we have the conditional expectation of x given f but now I will give you the spoilers. So you already know the argument as I have shown you before. So there's nothing to hide from you. So this is equal to the summation of the conditional expectation of x given fk times 1 over k, where each f sub k is a sigma algebra generated by fk. K equals 1, 2 through n. And this, by the probability number 2, will be equal to summation from k equal to 1 to n of this quotient times 1 sub fk, with the additional hypothesis that those p sub fk's are not equal to 0 or 1. So this is a statement of this proposition. So now let's start the proof. The idea is to use the proposition number 1 to first write the conditional expectation, which is f variable, into the sum with coefficients to be determined. And we will try to find those a sub k's through taking expectations, which is a trick that I have shown you before. So now let us carry out this idea. So let y in proposition number 1 be just the conditional expectation of x given f. this f. Which by definition of conditional expectation is f measurable. And now, by proposition number 1, we have this conditional expectation with respect to a finite sigma algebra as a form like this. The linear combination of indicator functions over each component. Now let's find a subcase. The trick is the following. We want to find this coefficient, and we have the information of f subcase. To single out each coefficient, we'll take the conditional expectation given the sigma algebra generated by those f subcase. So for f sub L, which is defined to be the subsequent algebra generated by f sub L, take the conditional expectation restricted to the set FL given the sigma algebra script f sub L on both sides. For the left-hand side, you get the expectation. There will be a double conditional expectation. So inside you get the conditional expectation of x given f times 1 over FL, which comes from here. And for the outer conditional expectation, this is conditioned on f sub L. This is the left-hand side. How about the right-hand side? The right-hand side is, so you're taking the conditional expectation of the sum times the indicator function 1 sub FL. So summation is from k equal to 1 to n. Again, this is conditioned on f sub L. And they are equal. So now let us look at left-hand side and right-hand side. Right-hand side is easier because if you look at this product, because f sub case are disjoint, so this is 0 if k is not equal to L. So the only term that is non-zero is the term when k is equal to L. So from right hand side you get, now you use the linearity of conditional expectation, which yields a sub L times the indicator function over f sub L. Left hand side is more complicated. To simplify left-hand side, we observe that the indicator function is f measurable because f sub l is in f. So we can put this indicator function inside in here. So the first step is because 1 over FL is f measurable, we have the first line of the left hand side is equal to this guy. And now, because f sub l is contained in the sigma algebra F, so this is a sub-sigma algebra of F by the Tower property of conditional expectation. We have this is equal to the conditional expectation with respect to the smaller sigma algebra. And again, because this indicator function is f measurable, so we have this guy equal to the conditional expectation of x given f sub l times the indicator function fl. What does this tell you? This tells you us any omega point in f sub l, we have the conditional expectation of x given f sub l evaluated at omega is equal to a sub l. This is from this equation. And now let us go back to this star equation. We know that a sub k is equal to this conditional expectation of x given f sub l over the set f sub l. So it follows that this conditional expectation of x given f is equal to the summation from k equal to 1 to n of the conditional expectations of x given f sub k's times 1 over fk. Here you should note that those fk's are disjoint. So this omega cannot be in both fl and fk for k not equal to l. And this finishes the first part of the proposition number 3. So how about this part? I told you this part follows directly from proposition number 2. That is because, but by proposition number 2, with A taken to be f sub k, where k is equal to 1, 2, through n, proposition number 2 tells us this conditional expectation of x given f sub k, where f sub k is a sigma algebra generated by f sub k has an explicit form like this, where a is equal to f sub k. And if you plug this back into here and observe that 1 sub fkc times 1 sub fk is equal to 0, because fk and fkc are disjoint. So if you plug this back into here, we get the summation from k equal to 1 to n with the coefficients given explicitly as follows. And remember, the meaning of this is the average of the random variable x in the domain f sub k. And of course, here we have implicitly used the condition that p sub fk's and p sub fkc's are non-zero. Namely, this is under the condition if p sub fk is strictly greater than 0, but strictly less than 1, for k equals 1 to n. Under this condition, we get this explicit formula for the conditional expectation of x given f. And we are done.